that it won't disturb anything in our
Okay.
system. Now, so from this formula, I can say electric field is equal to F upon Q naught. I think you have studied something or anything about
Yes.
vectors.
Yes.
So there must be definitions present also. So can you tell me what's the definition of electric field from this formula?
For the force per
It's
unit
okay.
charge.
In subjective exams, whenever we define a term, first of all, we write the term and their underlines, and then we say electric field or it is defined as. That's how a definition starts. Okay. Now, what I have done is I divided the force by a charge.
Yes.
So I will say electric field is defined as force experienced per unit test charge, right?
Yes.
Per unit means in division. Now, also electric field can also be stated as, let's just say the Q naught, this very unit charge, it's equal to +1 coulomb. Now,
Yeah.
what do you think will be the value of electric field?
Force.
Yes, exactly. So it will be equal to force. So I can also say that electric field is defined as force experienced. So you can see from now, I am just saying that electric field is force. Is it true?
Yes.
Electric field is not a force.
Yes.
So right now I'm saying electric field is equal to force experienced when? What's the condition?
When the charge is equal to 1 coulomb.
Exactly. When a unit test positive charge. Okay. First of all, unit. What is the meaning of unit here?
1.
One.
Yeah,
Like
the
right.
value. Yeah.
Exactly right. So when a unit test positive charge is kept in that field. So these are the two ways of defining a quantity. Like either you say it is force per unit charge or it is force when the charge is 1.
Yes.
Okay.
Yes.
Now, electric field due to a point charge. So the question is, or the derivation is that you have a charge small q and it is a point charge. Now you have to tell me what will be the value of electric field at this point P, which is at a distance R away from the charge. Can you tell me?
It's it isn't there like a kq over r squared, so
Exactly. So you might have already studied the Coulomb's law. Let's just
yes.
say here at P point, I have placed a charge Q naught.
Yes.
So what do you think will be the force between these two charges?
Uh the yeah,
Q1,
kq.
Q1, Q2 over the distance square.
Yes.
So now I can say electric field is defined as force per unit test charge.
Yes.
So divide this force by Q naught and you will get KQ over R square. That's the
Yes.
value of electric field, right?
Yes.
Now electric field is a vector quantity. We are sure of that. So if I say electric field is equal to KQ by R square, it doesn't match the vector form. On the left hand
Yes.
side, there is a vector, but on the right hand side, I'm not showing any vector. So what should I do?
Um make like
So which out of these quantity, K, Q or R represents a vector? Which one is a vector?
uh k
No,
q,
K and Q are scalar quantities.
so r.
R. This R
Yes.
is also called a position vector. if there's an arrow over it. Okay. So if I say here is the P point. So if you are looking from the charge Q, where do you think this P point will lie? You will say this P point will be in this direction,
Yes.
right? So this is a position vector. Now, to make any quantity a vector, you just multiply that quantity by a unit vector.
Yes.
Okay. All right.
Yes.
And what's the formula for a unit vector? How do you represent a unit vector?
I don't remember.
A unit vector is made by dividing a vector by its magnitude.
Yes.
So I can also say that it's KQR over RQ.
Yes.
So these are some of the formulas of electric field that you might have seen or not.
Yes, I've seen the first one, but not the KQR over R cubed.
Okay, this is also a formula because electric field is a vector quantity, so it must be in vector form.
Yes.
So the upper one represents only the magnitude. That means this is the value. It is the upper formula, the upper box is not showing you where is the direction of electric field.
Yes.
Now, they also teach you about graphs, that what kind of graph you will get with electric field and distance.
Yes.
Okay, right. So let's just say I have a point charge Q from which I am plotting a graph of electric field versus distance. So what kind of graph do you think we will get if I just plot a graph?
It will be like I don't know how to show, but it will be like 1 over x kind of like.
Okay, right. So we can see that electric field due to a point charge is given by KQ over R square.
Yes.
So electric field is inversely proportional to R square.
Yes.
So what kind of relationship do electric field and distance have? Direct or inverse?
Inverse.
Inverse, right? So if the distance increases, the electric field is going to decrease, right?
Yes. Yes.
So the graph would look like this one. Okay. That will be the graph. You can see that on this graph, if I increase the distance in this direction, in the red light direction, the distance increases.
Yes.
So electric field is decreasing.
Yes.
Like I have chosen a point P1 here. So the distance is low. You can see this distance is very much low. So the electric field is very much high.
Yeah.
Now, when I move away this point, let's just say I take this point P2 here. So now you can see the distance is bigger, but
Yes.
the electric field is smaller. So this graph is called a hyperbolic graph, or you can say hyperbola,
Yes.
right?
Yes.
You okay?
Yes.
Feeling a bit tired or sleepy?
No.
Okay. So that's kind of relationship as we get between these two. Now, let's just write another heading, which is called neutral point. So can you tell me what is the neutral point?
Where the electric field experienced is 0.
Exactly, yeah. So neutral point is a point where electric field is 0, or I should say net electric field is 0.
Yes.
Or you can say the force on a charge is 0. If you put a point charge at that place where electric field is 0, the force is also going to be 0. You can
Yes.
easily explain this by the formula. We know that force is equal to QE.
Yes.
So if electric field is 0, the force is also going to be 0. Now, let's just say I have two charges. First one is small q, other one is capital Q. And the distance between them is R. Now, small q into capital Q, this is greater than 0, or I should say small q into capital Q, the product is positive. So what do you make of that? Like the multiplication of two charges is a positive number. So what kind of charges do you have?
Like.
Like charges, right? So this is the condition of like charges. Let's just
Yes.
say we have two charges and both are like. Okay.
Yes.
So we have to find the value of a neutral point for like charges.
Yes.
Now, the small q, this represents smaller charge, that the magnitude of this charge is lower, and
Hmm.
that one represents bigger charge.
Yes.
Now, let's just say I have chosen a point P. So what do you think will be the direction of electric field due to small q at P?
Electric field.
Yeah.
EQ over P squared.
Let's just say both charges are positive. Now tell me, due to this charge small q, what will be the direction of electric field at P?
Away from, like, towards Q, like towards big Q.
Yes, right, that one. So I can say the electric field due to small q would be in the right hand direction.
Yes.
Now, what about the electric field due to capital Q?
Towards left, towards the left.
Towards left. So how did you know that the electric field from both the charges will be towards right or left?
Because like charges repel each other.
That point is correct, but I'm not showing the force of the capital Q or small q on the other charge. Repulsion will be on a charge. Now at P
Yeah.
point, there is no charge. At this
Yes.
point, we have no charge. So how do you think we will find the direction of electric field? So let's just
Yeah.
say I have a point positive charge, this one. So what's the direction of electric field due to a point charge?
Outward.
Outward, radially outward. So that would be the
Yes.
direction. So
Yes.
from a positive charge, electric field goes out. Now we have a charge small q, and you can see that electric field will go out in this direction.
Yes.
Also, you can say from the other positive charge, this q, electric field will move in this direction.
Yes.
So that's how we found the direction. Electric field will be outward, radially outward from a charge. Now,
Okay.
if at this P point, you want electric field to be 0, net electric field is 0. So what should be the condition?
EQ over P squared should be, like, I don't know, like the electric field by this and minus the electric field by that should be equal to 0.
Exactly. So we know that at P there are two charges. First one is the electric field due to capital Q, and then there is electric field due to small q, and that must be 0.
Yeah.
Now, electric field due to Q and electric field due to smaller q should be equal and opposite.
Yes.
The negative sign shows the opposite direction.
Yes.
So I can say if the electric field due to these charges is equal in magnitude in terms of positive sign, then the net electric field at P would be 0. Agreed?
Yes. Yes.
Now, let's just say the total distance was r, and I am assuming that distance from the smaller q is x. So what do you think will be the value of this distance?
Which distance?
This one. What is the value of distance between P and capital Q? This distance.
R minus x.
Exactly, right? So now tell me, what's the value of electric field due to capital Q at P?
K capital Q over R minus x squared.
Exactly.
I think we did these things last time.
You don't have this syllabus currently?
No, we did this during the last class.
In our last class, we studied this topic.
Yes.
Okay, no problem. So
yeah.
So what was the shortcut of of x, this distance?
R divided by under root Q, capital Q over Q plus 1.
Exactly. So that's right. So we already have done this topic. Okay, I totally forgot. No problem.
Okay.
It was a quick revision.
Yeah.
And what was the formula if the charges were unlike?
The same, except it was -1.
Right. So what more we studied in the last class?
I think we did this and then we stopped.
That was the last part.
We
Okay.
did, yeah. We did this and then we discussed why two electric fields do not intersect. And then we briefly discussed induction, but that's it.
Okay. No problem. So did we discuss that there are charges placed on the side of a square and find the net electric field?
I don't remember. I have no notes about that.
Okay, no problem. Let's just quickly solve another question.
Okay.
Let's just say that we have two charges, capital Q and capital Q, placed on the sides of a square diagonally opposite, and the
Yes.
square is of side A.
Yes.
Now, can you tell me what is the value of electric field at this point, at this P point? What is the value? What is the net value of electric field at point P?
It's towards the center, I think, but I don't know. Okay.
Okay. No problem. So what does the word superposition or superimposition refer to? What does it denote, superposition?
When, like in case of field lines, when two of them overlap or
Exactly, overlapping. So when there are more than a single charge, there will be a lot of electric fields.
Yes.
And how would you find the net electric field if you have multiple charges?
The
electric field is a vector quantity.
Yes.
And how vectors are added?
With their directions.
With their direction, you can say vector sum. So the superposition principle states that net electric field would be vector sum of individual electric fields.
Yes.
Okay, this one. Now, let's just say we have these charges. So this is charge number 1 and that is charge number 2. Can you tell me what's the value of electric field due to the first charge at P?
KQ over A squared.
Exactly right. And what would be the direction of this electric field?
Towards the left.
Sure.
Towards the right. Towards
the right. Yeah. Here is a positive charge kept and electric field would be outward from it. So at P, it will be towards right. So if you have studied about I, J, K vectors, unit vectors, how would I show this? I cap, J cap, how?
I cap.
I cap, right, exactly. So that would be the direction of electric field due to the first charge. Now, what about the electric field due to second charge? Where it would be?
KQ over A squared or J cap.
Exactly right. Now, so we can see that we have two electric fields present at P point.
Yes.
Okay, first one is in this direction and the second one is in this direction. So you have two vectors. So what is the angle between these two vectors?
90 degrees.
90 degrees, exactly. So now we remember a formula that if we have two vectors A and B separated by an angle theta, so the resultant passing between them will be given by square root of A square plus B square and plus, what was it?
2AB cos.
Exactly, it was 2AB cos of theta.
Yes.
Right. Now, you have two electric fields E1 and E2 with you.
Yes.
So we know that net electric field will pass somewhere from here.
Yes.
So what would be the value of net electric field?
Under KQ over A squared, the whole squared.
And now look at this one. Let's just say this value, KQ over A square, I'm calling it as E, capital E. So I can say that electric field E1 is equal to EI cap.
Yes.
and electric field E2 is equal to Ej cap, right?
Yes.
So net electric field would be A square plus B square plus 2AB cos of theta, right?
Yes.
So what is the value of cos 90?
0.
0. So our answer would be that net electric field is square root E square plus C square.
Yes.
That would be E root 2,
Yes.
right?
Yes.
So we had E as KQ over A square, and there would be a root 2.
Okay.
Can you just tell me what would be this angle? What's the value of this angle?
45 degrees.
Exactly. And why is that?
Because they are both of the same magnitude.
Exactly. So these both factors were of magnitude E and E. So the resultant would be an angle bisector of value E root 2.
Yes.
So if you have multiple questions like this, can you solve them?
I think so.
Okay, no problem. You can.
Okay.
Now let's just jump into the second question. Let's
Yeah.
just say we have again a square, but now some charges are kept. Okay, every corner there is a charge capital Q, exactly the
Yes.
same charge. And now you have to find what's the value of electric field at the center.
0. Put it.
The answer is exactly correct. So how did you say it would be 0?
Because the same magnitude is pulling is acting in from all directions.
Exactly, that's right one. So now we can see that, let's just say electric field due to this capital Q is E in this direction, right?
Yeah.
So electric field would be KQ over whatever this distance from center to the corner is.
Yes.
Okay, KQ over R square. Now that electric field would be in this direction due to the diagonally opposite charge
Yes.
E. And then these two electric fields are equal and opposite. So the electric field due to these diagonal charges will cancel out. And also you can see same will happen to the other diagonally
Yes.
opposite charges. This one.
Yes.
So the net electric field at center would be 0, right? So let's just say we have we have a regular polygon with us. Okay. What do you mean by a regular polygon?
With it has all sides equal.
Exactly. So that would be a regular polygon. And an interesting fact is that you can draw any regular polygon inside a circle. Whatever kind of regular polygon do you have? So let's just say our first polygon would be an equilateral triangle.
Yeah.
Our second polygon would be this one,
Yeah.
a square, and then
Yes. And then pentagon.
exactly there would be a pentagon, then hexagon, and so on. So each of these regular polygons can be drawn inside a circle.
Yes.
So what is a circle in terms of a polygon? You can say a circle is also a regular polygon, which is hard to digest, but it will be. As you can see, if the number
Yes.
of sides are increasing, the sides are going closer and closer to the circle.
Yes.
So a circle is also a regular polygon, but that polygon will have infinite sides.
Yes.
Okay, so in engineering, that's gonna help. Like if they give
Oh.
you have a polygon with infinite sides, so you directly have to think that the polygon is actually a circle.
Okay.
Okay, now,
Yes.
so let's just say in the first scenario, what I did was I put equal charges on each corners. So at the centroid, or you can say at the center of that hypothetical circle, what would be the value of electric field?
0.
0. And that's again in the next question. What I did was I put again equal charges on each and every corner. So what would be the electric field again at the centroid?
0.
0. And in the last scenario, again, I put equal and opposite charges at each corner.
0.
0. So you can say simply due to symmetry, the electric field at center would be 0. So that's nothing a hard question. It's not like it's very hard.
Yeah.
So let's jump on to the next question. Are you noting this now?
Yes.
Okay, please note it.
Yeah. Done.
Okay. So what kind of questions can come from this one? Let's just say you have a regular hexagon. Okay, yeah, perfect regular hexagon. Okay.
Yes.
Now, and the side of the hexagon is given as A. What I did was I put 5 charges at each corner. Now you have to tell me what's the value of electric field at center. Would it be 0?
No.
Because there's not a symmetry present.
Yes.
How would you solve it?
So it would basically be Q.
Q?
Because the other 4 get cancelled out, but this is Q is the only one that doesn't get cancelled out.
Exactly. Yeah, right one. So this can be explained due to symmetry. Let's just quickly see, like we have a polygon with, let's just say, n sides.
Yes.
N can be any number greater than 3 equal to 3. So we have a polygon, and what we did was we have put charges Q, 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 and Q on all corners except one. So this is the first corner, that one's the second, third, and this is the last corner, nth corner. So if I just hypothetically place a charge Q in here, you can say the electric field due to first charge plus electric field due to the second charge plus electric field due to the last charge would be 0 at the center. Agreed?
Yes.
But the charge on the first corner is not present.
Yeah.
So I can say the electric field due to the second charge, the third charge, and finally the nth charge will be equal to the opposite of electric field due to the missing charge.
Yes.
Right?
Yes.
Exactly. So let's just see. First of all, there is a small property about regular hexagon. Let's just say you have a regular hexagon with sides A. So what is this distance? What is the distance from center to a corner?
A.
A, right?
Yeah.
It can be proved. You can show that this triangle that I have formed will be an equilateral triangle. So all angles would be 60 degrees. So all sides would be equal.
Okay.
Now, in the above question, there was a charge missing from this corner. Okay, so we already know that this distance would be, so electric field due to this charge would be, electric field due to this charge Q would be KQ over A square, right?
Yes. Yeah.
And what would be the direction?
Along
this line, in this direction, you can say.
Yeah. Yes.
Now, we know that electric field due to all other charges, no matter how many they are, would be equal and opposite to this electric field.
Yes.
So we can see that if there was a charge, if here were a charge, electric field would be in this direction. So
yes,
the electric field due to all of these charges would be in this direction.
Yeah.
and of the same magnitude as that charge.
Okay.
So I hope you can also solve such kinds of questions.
Yes.
So that was the superposition of charges.
Yes.
Superposition of electric field due to charges.
Hmm.
Any doubt in this topic?
No.
Okay, right. Now we have electric field due to spherical charges.
Yes.
So spheres have a property. What is that one? A spherical charge behaves as a point charge. Okay, a spherical charge behaves as a point charge
Yeah.
for all points outside the sphere. Means you are not doing any calculation that's related to inside the sphere.
Yes.
Let me just quickly show you what I'm talking about. Let's just say I have a charge, a spherical charge, a big charge Q. And now I am taking a distance capital R, small r, which is greater than capital R. Means if the distance is greater than radius, you are definitely going to go out of the sphere.
Yes.
So I have taken a point P here. Now, all I ask you is what's the value of electric field at this point? How would you find?
K. Yeah.
So first of all, we know that this point is outside the sphere.
Yes.
For points outside the sphere, a spherical charge behaves as what? As a point charge.
Yeah.
So this question will show a behavior like instead of a spherical charge, we have a point charge placed in here. And from this point charge, we have another point P outside this sphere, which is at a distance R. So can you tell me what would be the value of electric field now at this point P?
KQ over R squared.
Exactly. KQ over R square. So you see, the spherical charges also behaves as a point charge. If the calculations are for the outsider points. So if this charge is conducting as well as non-conducting, it won't matter. The electric field at outside point will be KQ over R square. So please remember this for the later calculations.
Okay. Yes.
Yes.
Also, is R the distance from its surface?
No. The distance R, small r, it is always calculated from center to center.
Okay.
So if you are just told that you have a sphere which is placed at a distance small r, then you must always take the distance from its center. In different scenarios, he will explain that the distance taken is from the surface. Otherwise, if not mentioned, you must always take from the center.
Okay.
Now, I have written conducting and non-conducting. So let's just quickly see. If we have, let's just say, a conducting sphere.
Yeah.
So I think you know what are conductors. What are conductors?
They allow electricity to pass through them, or electric current to pass.
Exactly. So let's just say I have a conducting sphere. So this you must have read in the previous class. What is the value of electric field inside a conductor? Just quickly look from the notes.
Yeah.
Electric field, or I should say electrostatic field,
Mm.
inside conductors is always 0.
Yes.
Electric field is not present inside conductors. We will have a proof in the next chapter that why is that, also in this chapter. So electric field inside this one would be 0,
Yeah.
right?
Yes. Yeah, I think we discussed that because it tries to minimize repulsion.
Exactly, that one is right.
Mm.
So to minimize repulsion, the charges are always present on the surface of a conductor.
Yes.
So wherever you place a charge q, it is always going to go on the surface.
Hmm.
So now let's just say we want to calculate electric field due to conducting sphere. So we have a conducting sphere, this one. The value of charge present on it is capital Q. So while
Yes.
denoting conductors, do not ever write a positive or negative sign inside the
Okay.
circle, inside the spherical, because that would mean that the charge is present inside the sphere.
Yes.
So we always show the positive charge on the surface.
Okay.
Now, electric field inside a conducting surface is 0.
Yes.
Electric field outside is kq over distance square.
Yes.
And what do you think will be the value of electric field on the surface?
K Q divided by radius squared.
Exactly, right. Exactly right. Okay.
Okay.
Now, these are not always represented in terms of inside, outside, or on the surface. The condition that you might have been given will be like distance r is less than radius,
Hmm.
or distance r is greater than radius, or distance r is equal to radius. So that's
Okay.
how they may be told in a question,
Yes.
like in the form of distance. Now, can you tell me, if I am going to draw a graph between electric field and distance, what kind of graph we would have?
The hyperbolic.
Sure, hyperbolic.
For
It will be
yeah.
always hyperbolic, or after some distance it will be a hyperbola.
After we cross the radius.
Exactly, that one is right. So we have electric field and distance with us. Okay, these two things
Yes.
are present.
Hmm.
Now, for a spherical charge, the graph is going to change when you cross the surface,
Yes.
because just before the surface you are inside, and just after the surface you are outside.
Yes.
So we are going to draw the graph between electric field and distance. Now, quickly, when our distance is equal to radius, we would have an electric field with us called ES. That
Okay.
means electric field on the surface, and its value would be given by KQ or R square.
Yes.
Next,
Hmm.
as soon as we move away from the surface, the sphere is going to behave as a point charge,
Yes.
and electric field due to point charges was hyperbolic.
Yes.
So our graph would look like this,
Yes.
because electric field outside was equal to KQ or R square. We can also say electric field is inversely proportional to R square.
Yes.
And what was the value of electric field inside?
0.
0. So there will be no electric field, or you can say, you can draw this line touching the x-axis, this one.
Okay.
So if I again draw the graph between electric field versus distance, the graph would look like this one. Okay.
Yeah.
Such questions were asked a lot in IIT exams or some other competitive exams, like what will be the kind of graph you are going to get.
Hmm.
Okay.
Okay.
So can you remember this graph?
Yes. I wrote it down. Yeah.
What happens to the graph if the charge taken is negative instead of positive?
Isn't it the same
Electric field changes direction. And if
direction?
direction is changed, the quantity becomes negative.
Okay. So just in the is it flipped
Yes,
in
it will be flipped along the x-axis, or you can say
x-axis?
there will be a mirror image along the x-axis. So
Okay.
quickly, let's just say we have a spherical charge which is negatively charged, and the charge present on it is minus q. Now the electric fields would change their direction. So we have electric
Yes.
field and versus distance. So we know that the graph is going to change at the value r, capital R. So
Yes.
the electric field on the surface now would be minus kq over r square.
Hmm.
So our graph would look like this one. Okay. So just flip
Yeah.
the graph about x-axis. There will be a mirror image about the x-axis. Okay.
Okay.
So have you made this graph?
Yes.
Okay, right. Now, what's a shell? What is it?
Like a covering, like I don't know.
Shell is a very thin hollow sphere. Okay,
Yes.
like you have a solid sphere and then you made a cavity in it. Like you removed some part of it, so you can see the solid portion is present only in here.
Yeah.
So is this a shell? No.
No,
Why?
because it's not. It's not a very thin.
Exactly. So we will call this a hollow sphere. We won't call it a solid sphere or a shell. Now,
Okay.
let's just say I have a sphere and it is very thin. It is a hollow sphere and it is very thin. So all the mass of this sphere is present like on its surface.
Yes.
So this would be called a shell.
Okay.
Have you seen a bubble?
Yes.
So you can see the water or the soap solution is always on the surface.
Yes.
So a bubble represents a shell.
Okay.
What about the bowling ball? Is that a shell?
No.
A bowling ball is very much solid from the inside.
Yes.
Okay. So now, why did we discuss this term? Because it will be in syllabus. You will be asked like electric field due to a non-conducting shell. So now, instead of a conducting sphere, we have a non-conducting sphere,
Okay.
and which is a shell of radius r.
Yeah.
So tell me, if I'm going to give it a charge q, where will be the charge? Where the charge will live?
On the surface.
On the surface. The charge has no choice but to live on the surface.
Yeah.
So now, if you provide it a charge q, it has to be on the surface. Now, can you tell me what would be the value of electric field outside this sphere?
KQ over R squared.
What would be the value of electric field on the surface?
KQ over radius squared.
Exactly. And what should be the value inside?
0.
0. So you can see this one exactly matches.
Yeah.
Conducting sphere. Okay.
Yes.
So if you are asked to draw a graph of electric field versus distance, the graph would look exactly the same. Okay.
Yes.
Okay, and this doesn't look like a hyperbola. This one.
Yes.
So they have taught you in school this topic, right?
Yes.
Okay. Now, there's another term. Let's just call it shell effect.
Hmm.
So look, let's just say you have a shell
Yeah.
with you, and now you have placed a charge inside this.
Hmm.
So what do you think will be the net force on this charge due to the sphere?
0,
Why?
because it's being the charge is exerting force from all directions.
Exactly. So it's not at the center. Okay.
Yeah.
It can be anywhere inside. So a spherical charge cannot exert any force on the charges that are present inside it.
Hmm.
That's called a shell effect.
Okay.
Also, if there is a charge kept outside the shell and there is a charge inside, they won't attract. That is
Okay.
also shell effect. But I'll explain that in the later part of the chapter when
Okay.
we will cover induction.
Yes.
Now, why did we discuss it? Let's just go to the next topic. You'll see, right? Electric field due to non-conducting, uniformly charged sphere.
Yes.
So what kind of sphere do you have? A solid or hollow?
Hollow.
How?
Uniformly charged.
Uniformly charged. That means charge is present everywhere. The
Oh.
density is same.
Yeah.
So
Yes.
whenever you are told that uniformly charged, so this value specifically means that the sphere is a solid sphere. The charge is also present inside. Okay.
Yes.
Now, you must be aware about linear charge density, spherical charge, or volumetric charge density, these terms or not?
No.
Okay. Let's just quickly say, like, there's a first term, which is linear charge density.
Yes.
Linear charge density, this one. It is
Hmm.
represented by the symbol lambda. Let's just say you have a line, okay?
Yes.
And I have kept a charge along this line. So if
Hmm.
I increase the length of this line, the charge on this line is going to increase.
Yes.
So there will be a constant that would be lambda, and lambda is equal to Q over L. You can see the charge depends on length only. It doesn't depend on the area or the volume. It is
Okay.
directly dependent on the charge. So instead of defining all the three variables, length, breadth, and height, we are only taking one variable, which is length. So
Okay.
when I say linear charge density, that means all the charges along the length. So linear charge density, that means charge per unit length.
Okay.
Its formula, its mathematical formula would be dq over dl, or you could also say dq over dx, this one.
Okay.
So please remember what is lambda, because it will be used a lot.
Okay.
So now can you tell me what is surface charge density?
The charge per unit area.
Exactly. So we have another term with us, which is surface, or you could say superficial. Both of these terms can be used, or even aerial charge density. There are a lot of names.
Mm.
So surface, superficial, or aerial charge density. And do you know the symbol?
Yeah, one second. Is it like sigma?
Exactly. So this one is sigma. Like you have this white screen. So the charge is kept only on this white color. So you see if the white color increases, hence the charge will also increase. If the charge doesn't depend on the length or the volume, it's depending on the area.
Okay.
So sigma, that's defined as charge per unit area. Its formula is sigma is equal to dq over dA.
How do we know if like a charge is dependent on area or like?
First of all, it's a little tricky question. Like I have given you a plate. Okay. I say there is a plate on which a charge is distributed. So what is plate? A plate is two-dimensional, three-dimensional, one-dimensional. What kind of object is it?
Two-dimensional.
So in two-dimensional case, you will have to take sigma.
Oh, okay.
Okay. Now, if I give you like you have a sphere and I have distributed a charge on the sphere. So what kind of body is a sphere?
Three-dimensional.
So now you will have to take a three-dimensional density.
Ah, I see.
You will see a lot of examples to find out whether and which one to take.
Okay.
And finally, we have volumetric charge density. This one, represented by rho. So volumetric charge density, this one means charge per unit volume. The charge divided by the volume of the object or the charge. Okay.
Yes.
So now in the heading, I used electric field due to a uniformly charged sphere.
Yes.
So when I say uniformly charged, what would it mean?
The charge is the same everywhere.
Exactly. So which quantity is constant?
Density.
Density, exactly. So this one, our volumetric charge density, that one will be a constant,
Okay.
right?
Yes.
Now, let's just move on the heading. So we have a solid sphere. We have to mention that it is a solid sphere. So now I will have to show the plus or the minus signs in the sphere too. Because if it was conducting, these positive signs wouldn't be inside the sphere. Okay. Now, let's just say electric field at some outside points would be, what would be the value?
KQ over R
Our,
squared.
exactly. So in the first example, when I said electric field due to sphere, each sphere acts like a point charge for outside points. So I didn't mention there which kind of sphere we had. So it won't matter. It won't bother you.
Okay.
Whatever kind of sphere, like shell, conducting, non-conducting, whichever sphere you have, electric field outside it will be kq by r square.
Yeah.
The question can be changed. It can be like half of the sphere is charged positively, half of the sphere is charged negatively. Then you will have to solve it by different approach. But generally, that would be the case.
Okay.
So now, what will be the value of electric field on the surface?
KQ divided by radius squared.
Exactly. So these two quantities will be same for all spheres.
Okay.
Now the quantity that is going to change will be electric field inside. So do you think electric field inside would be 0?
No.
Exactly. How would you find electric field inside?
Uh, just um, wouldn't it also be? Would it be from the surface?
No, let's just see. How would you
Mm.
find? Let's just say, have you written this down?
Yeah.
Okay. Now, let's just say we have a sphere
Mm.
which is uniformly charged to Q, and the radius of the complete sphere is capital R. So now, can you tell me what is the value of density in terms of Q and R?
In terms of Q and R, dq over r cubed.
It is uniformly charged. So dq over dv would be exactly as q over v.
Yes.
Okay. So if density is constant,
Ah.
both of these quantities will be same. If the
Yeah.
density was different, these quantity would be different.
Mm.
So now rho would be charge per unit volume,
Yes.
right?
Yeah.
Okay. Now let's just say I have taken a distance from the center, which is small r. So now just draw a hypothetical sphere. We have drawn this hypothetical sphere, and this hypothetical sphere captures a charge of plus small q.
Mm.
So do you think that the whole charge will be responsible for the electric field at this P point, or just the charge that is inside the hypothetical sphere? Which charge will
Uh,
have electric field at P point, the whole charge or the smaller charge Q?
the whole charge,
Why?
because the
Okay,
charges still exist. Yeah.
exactly. No problem. No problem. Let's just say I have a shell.
Mm.
Okay. On this shell, there is a charge Q. So what will be the electric field inside this shell?
Uh, z-
0.
0. Yes.
0. Now, the point P is here. Let's just say I have made made a shell, this one.
Ah. Okay.
So these parts would act like a shell or a
Yes.
combinations of a lot of shells. And electric
Yes.
field due to these shells will be 0.
Yeah.
So electric field at R at, at P would only depend on small q.
Yeah.
Not only, it will also depend on the distance R. Let's just say it will depend on q. Okay.
Yeah.
So I can say q would be this one or not.
Yeah.
Density is same whether it comes from the whole of the sphere or just from the hypothetical sphere.
Hmm.
It would be same, right?
Yes.
Right.
Yeah.
Okay. Now, electric field at P point would be kq over small r square. Agreed?
Yes.
Sure.
Yes.
Okay. Now, can you tell me the value of small q from here? Put the value of small q in terms of capital Q, because we know the whole charge. We don't know
Mm.
the charge that is present inside it. So put the values, please.
Uh, isn't small q equal to capital Q?
The radius are different.
Ah, the radius. Okay. Yes.
So k by r square would be taken common out, and small q would be q r cube over r cube,
Yes.
right?
Yes.
Okay, please write it down.
Yeah.
Okay, no problem. So what's the value of electric field inside?
Um. Just 1 minute. I'll try to find it. K. It'll be K. KQR over R cubed.
Exactly, right, this one.
Yes. Yes.
So have you written it?
Yeah.
Okay, right. So what's the relation between electric field and distance now from this equation?
It's inverse, but it's like 1 over x cubed. Like,
Are you sure it is inverse? Because when I say find the relationship between electric field and distance, I didn't say radius, I said distance. So which
distance
symbol here represents distance?
or small r.
Small r. So you should say electric field inside is proportional to small r.
Oh, okay.
Okay, and that's also another important point. Please do remember it.
Yeah.
Okay. Now, a punishment for you is plot the graph. You
Okay.
have electric field versus distance for a non-conducting uniformly charged sphere.
Would it just be linear graph?
Okay, first of all, you know, for spherical charges, the graph changes at the radius, right?
Yes, yes.
Now, please draw it.
Okay. Yeah, I drew it.
So what kind of graph would you have?
So the graph is like a linear from until R and then hyperbolic going down.
Exactly, right one. So now we have electric field on the surface. So first we will have a linear graph because electric field inside is proportional to R, right? And
Yes.
then when we go outside the sphere will behave as a point charge, and for point charges, there are hyperbolas. So the graph would exactly look like this. So have you read these things?
No.
Okay,
But
so
I think we just brushed over it. We didn't really, I think, look much into detail.
well, if you haven't, then you are very smart. You are answering these questions very fast. Okay, so that's a good thing.
Okay, thank you.
Now, for a non-conducting sphere, we have three formulas for inside, which are represented in different senses. So first of all, we had electric field inside as KQR over R cube. So you can change this formula as KQ over R square into R over R. Any problem?
No.
So what value does KQ over capital R square, the first bracket, denotes?
The electric field outside the circle.
Outside the circle, because we have used capital R.
Yeah.
So first one is
on the surface.
on the surface. So you can say electric field is given by this formula. It is also another formula.
Okay.
Okay. Like in some questions, if you are given the electric field on the surface and then you are asked what would be the value of electric field inside. So you could start from this formula.
Okay.
Okay. Now, again, that one is another important formula for the questions that we will discuss later on for cavities.
Okay.
We have electric field as KQR over R cube. That was the formula that we derived.
Yeah.
Now, please write K as 1 over 4 pi epsilon naught. I think you are aware of that.
Mm.
So I can write this formula like this one. Sorry, I made a
Oh,
mistake. The R should be upward now, right?
yes.
So is there a quantity like 4 pi r cube?
The density.
Yes,
No, volume,
but
volume.
4 by 3, it should have been
Ah, yeah, 4
4
by
by
3.
3 pi r cube. Now
Yeah,
we can see that it's qr over 3 times volume times epsilon naught.
yeah.
And charge upon volume is what?
Charge, volume.
Charge per unit volume. It was kind of a
Charge
density.
per, yeah, density. Volumetric density, rho.
Exactly. So we have another formula.
Okay.
And this formula exactly comes in the vector form.
Yeah.
Okay.
Yeah. I had a question. What exactly is epsilon?
Epsilon naught. This one.
Epsilon naught, yeah.
First of all, look. This symbol, and this symbol. These all symbols are called epsilon.
Okay.
They are in Greek. So if you know Greek, I
Yeah.
don't. Now, so this symbol here, like C, and there is a bar in between. This symbol is called epsilon.
Hmm.
And then there comes this, like you have punched it and it just swelled.
Yeah.
So there is this symbol which is called naught,
Yeah.
NaUGHT, naught.
Hmm.
So this is the not that naught, NOT.
Okay.
So this formula is called epsilon naught.
Okay.
Some authors also called it epsilon zero, but I don't. I'm not from those authors.
Okay.
So now this is epsilon naught. Now, what's the physical name? What's the name that we give this symbol in physics? So this symbol is called permittivity.
Hmm.
Are you aware of this word permit?
Yes.
So if you have to go somewhere secure, you have to have a permit.
Yeah.
So from that word permit, we get another word called permittivity of free space.
Okay.
Look, let's just say you have a positive charge. And from a positive charge, there are many electric field lines originating from it, like this one.
Yeah.
So let's just say these are 80 lines.
Hmm.
These are 80 electric field lines.
Yeah.
And these lines are present in vacuum.
Hmm.
Now, what I did was I took this charge and then I placed this charge in water.
Yeah.
So now in water, there was only one electric field line. So
Why?
now we have two media. One is
Yeah.
vacuum, other is water. So they
Yeah.
both have different permittivities. They both allow different number of electric field lines to pass through them.
Okay.
So
But
yes,
do electric field lines require a medium to travel?
what would be your opinion on that?
I don't know
Do they?
because when
No,
we did
no, they don't.
yeah,
Your answer is correct. Electric field is from electromagnetic waves, and
yeah,
electromagnetic waves don't need a medium to propagate.
yeah.
But electric field is passing, the number of electric field lines have changed.
Okay.
Uh, Listen, in
Mm.
water, there are 80 electric field lines present, but
Yeah.
there has been some induction of water too. Water also has developed some electric field of its own,
Okay.
which is canceling out the electric field of this charge.
Oh, I see. Okay.
So there is a relation which says the net electric field due to the net electric field is equal to external electric field plus induced electric field.
Okay.
So again, you'll have to wait for it, like in the
Okay.
chapter that has capacitances. Do you have capacitances in your syllabus?
I don't know. Maybe I think
It's
so.
okay. It's okay. No problem.
Yeah.
So someday you will
Yeah.
surely study that. Why is that?
Okay.
Okay. So epsilon naught, that tells you how much a medium is going to allow the electric force or the electric field lines to pass from it.
Okay.
So I think you know the value of epsilon naught.
Yeah. Yeah.
What's the value?
I don't have it memorized, but I have it written down.
Well, you should. You should. Epsilon naught is equal to 8.85 into 10 raised to power minus 12
Okay.
coulomb square per Newton meter square. I think that's the unit. Okay.
Yeah. Yes.
Okay, no problem. Now, there's a question. So I don't think so that I should jump just right away in a hard question, but I will.
Okay.
So you are given a non-conducting uniformly charged sphere.
Yes.
You have a sphere which is uniformly charged to volumetric charge density rho.
Yes.
Now, what you did was you made a cavity. You made a cavity in this. Cavity means you took out some charge, you took out some part of this sphere.
Yeah.
Now, let's just say the cavity is circular. The question will be much simpler. You took out a charge. This space is now completely blank. You can say this cavity is vacuum now. Your question is, what is the value of electric field inside the cavity? This is a most basic question that is asked again and again. And nobody asked this in competitive exams. Just they asked that in school. So what's the value of electric field inside this cavity? Is it a constant? It should be a variable.
Like a constant.
Okay. So this question is solved like this one. Yes, it will be constant. The answer is right. Let's just say you have chosen a point P that can be anywhere inside this cavity. Okay. And this is the center of the sphere, and it's the center C dash of the cavity. So let's just say we know that this distance is R.
Yeah.
So electric field at a distance R would be equal to rho R over 3 epsilon naught.
Yeah.
Right?
Yes.
Now, let's just say that this distance is R dash.
Sorry, I have a question. How did we get rho R over 3 epsilon naught?
And that's a very good question. Let's just back it up. Okay.
Yeah.
So if you have a solid non-conducting sphere, electric field inside it at a distance R would be given by this formula.
Yeah.
Now we have electric field at distance R. So due to cavity, let's just say the cavity was not there. So due to cavity only, what would be the value of electric field at P? It would be rho R dash over 3 epsilon naught.
Yeah.
Right?
Yes.
Let's just call this distance as A, because why? Why? Because we always take the distance of points where we have to find electric field as R. So this distance, I must have taken that as R.
Okay.
Now, no harm done.
Yeah.
So what do you think will be the value of electric field at P? So we can see if I go to this one, I go to electric field at R, this one directly.
Yeah.
Electric field would be ER.
Yeah.
Sorry, just a minute. Huh. Minus, there is a cavity. If you remove a charge, how do you think the electric field would change?
It would, I don't know, reduce.
It would reduce.
Yeah.
So if you have a charge and you then just remove some part of charge,
Yeah.
let me just start that in a simple sense. Let's just say we have a sphere and it is positive charge, and now you know the electric field at this point P.
Yeah.
Now, what happens if I cut this spherical charge? How would you
You.
find the electric field? You will just subtract the part that is broken, that is removed,
Yeah.
right?
Yes. Yes.
Now, so electric field of cavity, if the cavity was not there, would be
Yeah.
this one. So I would just subtract this E. Let's just have this symbol as C dash.
Yeah.
And if this cavity was not there, like I had given you this question, you have a center here and you have a point P here.
Mm.
This is electric field at R. So
Yes.
you would directly say that ER is equal to rho R over 3 epsilon naught, this one.
Yes.
So these are the three symbols.
Mm.
First, find electric field that should be there
Yeah.
when there is no cavity.
Okay.
Then find how much electric field you will lose if you remove a cavity.
Okay.
So this should be the value when electric field was there.
Yes.
This value has been removed, so subtract it.
Hmm.
So what would you get? Put these values, please. So we have rho R over 3 epsilon naught minus rho R dash, sorry, R dash over 3 epsilon naught. So now we have rho 3 epsilon naught and R minus R dash. This one left with us. So let's just quickly look at these diagrams. First of all, we had this distance as A, then this distance as R dash, and this distance as R.
Yeah.
Can you tell me what's the vector relation between these three vectors, R dash, and A?
R is equal to under root R squared plus A
No, no, no,
squared.
just in the
Sorry.
vector form. We can say this one.
Plus. Yeah. Yeah. Yes.
Now, can I say R minus R dash equals A?
Yes.
So we had in the above relation R dash. So
Okay.
that's the exact value that I first wrote.
Okay.
Just first of all, please write it down. Then I'll
Yes.
explain again. It was kind of a difficult question for a beginner.
Oh. Yeah. Yeah. Done.
Let's quickly see what was the moral of the story.
Okay.
First of all, let's just say you have a spherical charge of charge density rho.
Hmm.
Then there is another spherical cavity present inside the sphere.
Okay.
So always find the distance between centers.
Okay.
So find this vector A.
Hmm.
This is a vector. And now consider any point inside this cavity. So let's just say I have a point P here.
Yes.
So I derived the value of electric field as rho A over 3 epsilon naught, this one.
Yes.
So was the value of electric field at P point depending on where the P point was in the cavity?
No.
No. So the electric field at any point would be exactly in the same direction as
Yeah.
this one. So
Yes.
electric field inside cavity everywhere would be given by this formula.
Yeah.
So inside a cavity, electric field is uniform.
Yeah.
Okay. So today we have studied, let's just quickly revise a lot of things.
Yes.
So first of all, we had the value of electric field, the definitions of